So here is lesson 2 for torque. This one should be a little bit shorter than the first one. Basically, we're just going to look at what it means. So when we were talking about forces, we were talking about equilibrium. We're now going to look at what it means for things to be in translational as well as rotational equilibrium. So this thing is not moving up, down, left, or right. Translational. So this thing doesn't move up, down, left, or right. If it's in translational equilibrium, rotational equilibrium, the thing doesn't spin clockwise or counterclockwise. There is no other way to spin. So if it doesn't move, or to have translational equilibrium, the forces must be balanced. For it to have rotational equilibrium, the torques must be balanced. So then there's questions like, just conceptual questions like this. So is it possible for an object to be in translational equilibrium, i.e. it's not moving up, down, left, or right, but not in rotational equilibrium? Pause it here for a sec, maybe. Think about what that would mean. It means, can an object spin without it moving up, down, left, right? Well, hopefully you've had a chance to think about it. The answer is yes. You can be in translational equilibrium, but not in rotational equilibrium. So something like a Ferris wheel would be an example. These things spin without rolling down the street. It would be terrifying to be on a Ferris wheel that was just like kind of rolling down that would be awful. A washing machine or a dryer, something that spins, hopefully without moving down or moving across the room. So let's look at these guys here. What do these forces do to these objects? So the diagrams below show beams in from a top view on a frictionless table. So this is the table surface. We're looking down on it, just like I am right now. So gravity is into the page, normal forces up out of the page, so we can ignore those for each one of these questions. We want to specify the type of equilibrium for each beam. Translational, rotational, both, or neither. For the torques, we want to take the pivot to be the center of mass. And so for each one of these, our pivot is going to be right there, at the center of the mass, for each one of these things. So think about what's going to happen here. An easy way to do this is to actually take an object and do to it what the picture is demonstrating. So if my pivot's here in the middle, and I've got a force this way and a force this way, what happened to my pen? Did it slide up the page or down the page, left or right? Well, no, it just spun. So this thing we would say is in translational, it has translational equilibrium. It does not have rotational equilibrium. So then this guy over here, I have a force downwards here, and I have a force that I'm going to pull downwards here. So it slid down. So this thing has rotational, or it's in rotational equilibrium, but it does not have translational equilibrium. It's going to slide down. This guy here, this force upwards it's at the pivot, force upwards at the pivot and downwards here means it's not going to slide up or down the page, but it is going to spin. So again, this thing is in translational equilibrium. For this guy here, what's going to happen? This is going to be harder to demonstrate. I've got a force upwards, I've got a force downwards here. So this is actually going to look like this. I'm pushing down, I'm pulling down, and I'm pushing up there with my thumb. The object is not moving. It's not spinning, it's not sliding. So this one has both kinds of equilibrium. So this actually allows us to look at a bunch of different questions. I'm going to do 2 examples, and then you guys are going to launch into some homework. So here we go. We have a 100-gram meter stick. We're told it's in rotational equilibrium, i.e. it's not spinning, which means my clockwise torques equal my counterclockwise torques. The numbers above the stick represent centimeters along the stick from the left end. So this thing's at the 15 centimeter mark. That's at the 95 centimeter mark. And important to demonstrate is that, or not to demonstrate, but to remember that 100 grams is 0.1 kilos. We need to be in kilograms for this. We're also going to need to want to be in meters. So if these are centimeters, that's centimeters. This is going to be 0.15 meters, and this is going to be 0.95 meters. May as well do those conversions right now. We want to draw a free body diagram, and then we want to write a balanced torque equation and find the missing mass required to balance the beam. We're given the pivot. The location of the pivot's here in the middle. So yeah, let's draw some forces. There's a force downwards here. We're told that that's 100 grams. So this is also 0.1 kilograms. This distance is 0.15 centimeters, and the pivot's right there in the middle. So this distance here, again, we always want the distance from the force to the pivot. So this is going to be 0.35 meters, or 35 centimeters. And this distance over here, may as well toss that in there here while we're working on it. 50 to 95 is 45 centimeters, or 0.45 meters. So the force of gravity downwards here is going to be the 0.1 kilograms times 9.8, so that's going to be 0.98 newtons. And this is the mass we don't know, but we do know that there's a force downwards there. Fg here is going to be 9.8 m, because we don't know what m is. That's what we're looking for. There's two more forces acting on this thing that we have to consider. There's a normal force acting upwards, and then there's the force of gravity here acting downwards. Force of gravity acting downwards, we're told it's a 100 gram or a 0.1 kilogram beam. So this is also going to be 0.98 newtons. But we don't know what the normal force is because we don't know what this mass is. But now our free body diagram is now complete. We just don't have that value. So let's go ahead and approach this question. We're told that this thing is in equilibrium. I think I spelled that right. So if it's in equilibrium, let's make that Q look more like a Q. We know that the torques clockwise have to equal our torques counterclockwise, because the net torque equals 0. I should have put that up there first. So my clockwise torque, well, which one of these is going to be clockwise? This guy here, if I look at what it's doing, if I ignore this, this thing's going to spin downwards. So this guy here is my clockwise torque. Going to cause a clockwise torque. This guy here is going to cause my counterclockwise torque. So I've got F perpendicular R equals F perpendicular R. Both are, forget that, that shouldn't have been there. Sorry. So we can see these are both perpendicular to the beam, so we're good to go. This one's going to be 9.8 m times 0.45, the distance from the force to the pivot. And that's going to equal 0.98 times 0.35. So then my mass is going to be 0.98 times 0.35 divided by 0.45 times 9.8. We can go through, we can solve this. This should be 0.078 kilograms. So then the mass of this object is just going to be 78 grams. And that's it. We're using the fact that this object is in equilibrium to tell us the net torque is 0, so my clockwise equals my counterclockwise, and then that allows us to go through and solve it. What do we do here? So until now, I guess the first lesson in this first question, the pivot points were obviously located. So all the torque problems we had an obvious pivot point, but what do we do with something like this? What about objects which are at rest that don't have an obvious pivot point? So a person in push-up position, you could put the pivot here, you could put the pivot here. If you're crazy, you could really actually put the pivot at the center of mass. Where do you choose? Now this is where this unit becomes a lot more tricky. You are the one now that has to decide where the pivot point actually goes. Well, it doesn't actually matter, believe it or not. In actual fact, they can all be used as long as the object is not moving. That's important. As long as the object is not moving, any point can be used as the pivot. And so now it becomes advantageous to use certain locations over others, and you're going to see why here. I sometimes describe this as weaponizing the pivot point. You can use the pivot to eliminate parts of the problem that become difficult to deal with. So let's approach this problem and place the pivot point kind of wherever we want. So the person in push-up position below is at rest and so is in rotational and translational equilibrium. We like this. They're not moving up or down, they're not spinning, they're not moving left or right. They're static. We're told here to use the toes as a pivot point to find the force on the hands. Okay, well, let's go through and do it. If I put my pivot point here, like there's so much that we don't know. We don't know the force on the toes, we don't know the force on the hands. The only thing we know is that the gravity is acting on this person, pulling them down. If I put the pivot point here, what this is going to do, I'll call this F toes, this is F hands. By putting the pivot point here, we've already said that forces acting on or acting at the pivot point don't contribute to the torque. So what this does is it allows us to ignore that force and only consider these two and use the torque equation to compare these two. If I'd put the pivot here, we could have ignored the force on the hands to find the force on the toes. You want to use the pivot point to eliminate forces you don't know. That'll be your goal here going forward. So if this guy is in rotational and translational equilibrium, we can go through now, we can figure out what that means. So we've got this idea here of total equilibrium. That's going to let us do two things. First of all, what that's going to tell us is that my torques clockwise equal my torques counterclockwise. So if my pivot's here, what two forces are going to cause torque? Well, that guy there and this guy here. My hands are pushing up, which means it's going to cause a torque that way. The center of mass or gravity is pulling me down right there, so this is going to create a torque this way. So this one's going to be clockwise, this one's going to be counterclockwise. So my clockwise torque, again, all F perpendicular times that, R, this is, again, just reinforcing the formulas here. My force is for my clockwise torque is 700 newtons. And again, R is always the distance from the pivot. So we put the pivot at the toes. The distance from the toes to the center of mass is 50 centimeters. So 0.5 meters. And now I want the force from the hands and the distance to the pivot. Well, the distance to the pivot is 80 centimeters or 0.8 meters. So now we can go through and we can find the force on the hands. And divide by 0.8. Divide by 0.8, and I find that the force on the hands, or from the hands pushing up, is 437.5 newtons. So now we figured out the force from the hands. Put that up here, 437.5 newtons. And now the question says, okay, write a balanced force equation to find the force on the toes. You won't be given problems that outline it this specifically, but this is giving us a method. By putting the pivot here, we eliminated the toes. We used this gravity to find the force on the hands. The pivot is still here. I mean, I could move it to the hands now, and I could use the torque equation again, except now this is going to be a counterclockwise torque, and this would become my clockwise torque. Or I can leave the pivot here, and I can use the fact that I'm in total equilibrium to tell or to say that my forces up equal my forces down. Well, what forces are up? If I look at my diagram here, I've got two forces up, toes and hands. So the force from the hands plus the force from the toes is going to equal my forces down. Well, I have one force down, that's just Fg. So my force from the hands is 437.5 newtons. The force from the toes is what we're looking for, and Fg we're told is 700. So then F toes is just going to be the 700 minus the 437.5. That's going to give us 262.5 newtons for the force on the toes. And we're done. Using total equilibrium, we were able to use both the torques and the fact that this thing was in translational equilibrium to figure out both hands and toes. If I'd put the pivot here, the process would have been exactly reversed. I would have used the torques then to find the toes, and then I could have used my forces up equals forces down to find the forces on the hands. It would have just flipped the question. I'm not going to do this example here. This is putting the pivot in the other side. If you want, you can prove it, do it, try it, prove it to yourself. You could put the pivot here instead and approach it the exact same way. These are problems we looked at before. Not all problems require balancing torques and forces. In this particular problem, this was back in Unit 2, Lesson 9, we had an object hanging, leaning up against a wall, so there was a tension. We're told that this is 8 degrees. There's a tension up here. There's a force acting downwards. There's a force acting off the wall. I'm not actually going to do this equation or this example, but we could use torques if we wanted to here. This would become my pivot point. But we looked at this exact same kind of question before, back in Unit 2. So you can approach these things multiple ways depending on the kinds of questions that you're given. And that's it. These ideas of translational versus rotational equilibrium are relatively straightforward. I believe you just got to make sure you take the time to step by step go through these things, making sure they make sense to you in your head. So what I want you guys to do here is I want you to question 1. There's a lot to question 1. All 6 of these are question 1. I want you to do question 3. There's 4 objects there in question 3. I want you to do question 4. I want you to do question number... or try question number 10. And I want you to do... question number 11 is good as well. So it's just those 5. I know question 1 and 3, there's a lot going on there. The only way you're going to really wrap your head around these things is to do this practice, though.